Hi, let's summarize everything that we've done thus far with customer's choice model. So, we are assuming that the utility function depends on the quantity of good X and Y that customer consumes. Then, we are acknowledging that customer is binded by budget constraint, which means that customer encounters prices of the two goods. So the customer takes them as a given, so they're going to be exogenous in our model. While similarly, B, his income, is also treated as a given. This is a typical problem of optimization under constraint because we want to find X and Y that maximizes the utility given the budget constraint. So we use Lagrange multiplier, so we build the Lagrange function. We've calculated the first order condition. Out of the first order condition, we found out that at the point where customer maximizes his or her utility, the ratios of marginal utilities and prices are the same, or in other words, the slope of the indifference curve or marginal rate of substitution is equal to the slope of the budget constraint. And at this point, if customer purchases this much of good X and this much of good Y, the utility will be maximized. How do we know that it's going to be maximized? Because we also calculated the Hessian and we established that as long as the shape of the indifference curve is convex, we can be sure that this is a maximum. Okay, and look, we also said before that lambda that we calculate over here has an additional interpretation, right? Because lambda is giving us comparative static derivative due to relaxation of the constraint. We see that in here that this expression for lambda is telling us what is happening to customers utility when budget is increased by $1 additional. So this lambda in our case represents marginal utility of money, and from that we see that in equilibrium ratios of marginal utilities to prices for each good should be exactly the same as marginal utility of money. Okay, and basically this is all we said thus far in a nutshell. However, we also know that once we found that the equilibrium exists, we can use implicit function rule, right, on these equations in order to calculate comparative static derivatives. Okay, so let's think what is exogenous and endogenous in our model. Well, prices are given to the customer, and we are assuming that the customer is facing a certain budget. So those three are definitely exogenous, and within these circumstances, our customer needs to choose the level of X and Y that will actually guarantee the highest possible utility. Okay, so look, over here we have a system of three simultaneous equations, right? And we know that this system is true for the equilibrium, right? So we can write it as B minus P x times x minus P y times y equals to 0, when of course, x with asterisk and y in asterisk represents optimum values, so optimum quantities of good x and y. Then we have ux times x y minus lambda dx equals to 0, y lambda p y equals to 0. Now, what we need to do with this system is to calculate its total differential. Look, in this model, we've got both exogenous and endogenous variables. As we stated before, budget and prices are exogenous. Customer is getting certain income and can do nothing about it. Then prices, of course, are dictated by the market. They are definitely beyond the control of the customer. What customer does is chooses x and y in such a way as to optimize, as to maximize his utility, and as a result, of course, this changes the marginal utility of money of this customer. That is, so what we now need to do is to differentiate the system with respect to all 6 variables, right? Exogenous and endogenous. Okay, so out of this we get dp, right? When budget is changing, it changes by dp. Now, here we need to use the product rule, so we get this is negative px dx with asterisk minus x times d px. Right? Of course, as a product, you can change as a result of changing x or in price of x. Right? This is spending on good x. Of course, it increases with higher quantity purchased or with the higher price. And the same we got for y. So we got this is py times d y with asterisk minus y with asterisk times dp y, and it's equal to 0. Now we go to the second equation. We differentiate ux with respect to x and y. So we get u x y. I'm already writing it in xy as I would do here. We know based on Young's theorem that cross derivatives are the same, so this will make one less expression on the black one. Okay, and here again we use the product rule. We get minus lambda d px plus lambda lambda dpx px d equals to 0, and very similarly for the last equation. Minus, I'm sorry. Okay. Now that we have this system in differential form, we should, as usual, organize endogenous variables on the left-hand side. Our endogenous variables are, of course, associated with changes with x, with changes in y, and with changes with lambda. So if we cross all of those, we see that actually we've got only 5 exogenous terms over the system when everything else is endogenous. Okay, so if I organize now everything everything endogenous exogenous on the left hand side, everything exogenous on the right hand side, we get negative px dx minus py d y equals negative d b plus p x d plus x dp x plus y dp y. Okay, then starting with expressions with lambda, we would have negative px d lambda. Then we will have plus. Let me write it a little bit further here. We will have plus ux x d x plus uxy d y, which is equal to lambda times dx. Now, over here, we will have very similar situation. So we get this is negative p y d lambda plus a uxy d x plus uy d y equals to lambda dp. Now, this system can be easily transformed into matrix notation. And this is what we're going to do next. Because actually, as we remember, dealing with systems of differentials using matrix notation brings a lot of advantages. Okay, so first, we start with the matrix of coefficients is negative 0, negative px, negative py, so negative px, negative py, uxx, uxy, uxy, uyy. Here we have d lambda, d x, d y. Okay, let's make it a little bigger. We have some plans for it for the future. And finally, we rewrite all the exogenous terms from the right hand side of the equation. Okay, so we got let's change the order to make it shorter. Dx plus y dpy and minus dp. And then finally we get lambda dx and lambda dp. Okay. Now, look, this system has, as we said, a lot of advantages. First is that this matrix, if we calculate its determinant, we're going to get a bordered Hessian, which happens to be a Jacobian for this system, right? And it also, so it actually, we get everything we need right on the left hand side. We've already established that as long as our indifference curve is convex, we will have Hessian and Jacobian. That is positive, which means it's different than 0. And because this is the case, we know that this system implies 3 functions. Functions of lambda, which is marginal utility of money, as a function of price of good x, price of good y, and budget, similarly as well for good x and for good y. Okay, so now that we know that that this system implies those functions, we can calculate their comparative static derivatives. And look, we can now use these comparative static derivatives to see what happens when one of the components of our model, exogenous components, is changing. So we're going to start with a change in customer income. Okay, so how do we model this situation? Exactly the way we did when we used implicit function rule previously. So first thing we need to do is we need to assume that budget is changing. It increases. In our case, you can think about it as positive dp, right? But what is important for us is that it's not negative, not equal to 0. And at the same time, not to get too confused with the effects of other variables, what we should do is to assume that price of good x and price of good y remain at the same constant level. And look, this actually makes this entire system of simultaneous equations very, very easy. Why? Because the right-hand side reduces to just 3 numbers. Look, this, if price is not changing and prices are not changing, then this expression is 0, and this expression is 0, as well as this expression is 0, and this expression is 0. So we are just left with negative dp, 0, 0. Now look, because we are assuming that budget is changing, right? Customer's income is changing, we can divide both sides of this equation by dv. And over here, we're going to receive comparative static derivatives that we want. Okay, now, look, the only thing we need to do now is to calculate this comparative static derivative in exactly the same way we did it before, so using just Cramer's rule, right? So, what we were looking for is what is the impact of increase in budget or in customers' income on spending on good X. So, in order to calculate it, what do we need to do? We need to take this determinant, take out of this, take determinant of this matrix, take this vector and replace the middle column, right? So negative 0, negative px, negative py, negative 1, 0, 0, negative py, u, xy, u, y. And of course this whole thing divided by multiplication. Now look, it's really easy to deal with this issue of solving this problem because we clearly see that by using Laplace expansion with respect to the middle column, we get very nice and clean expression 1 over multiplication times negative px, negative py, ux, y, u, y. However, okay, let's calculate it all. So D. Okay, we get that this is u x y times p y minus u y y times px. Okay, and look, here is where we encounter our first problem. Because look, we know that this expression for Hessian is definitely positive. We we are assuming that we got a maximum, right? Budget, indifference curve is context. Then we also know that prices must be positive, and we also know that we are encountering decreasing marginal utility, so UIY needs to be negative. And look, with this, we obtain that this entire expression here is positive. However, what we don't know is what is the sign of UXY. We have not assumed it yet. And look, just because we don't know what is the sign of this, this makes the sign, this is what makes the sign of this entire expression indeterminate. Right? And look, how does it relate to what you learned in microeconomics? Look, you learned that when customer's income increases, customer purchases more of luxury goods and normal goods. However, if we are talking about inferior goods, customer should be purchasing less of them. And this is what we would see through this expression. If this expression is negative and sufficiently big, we would expect that this could turn negative. However, of course, this is an unusual example of the Giffen's good that are actually so inferior that we would get the negative outcome. So customer gets more money, and even though the customer is purchasing less of that good. Okay, and look, I could make a very similar calculations for derivative of the quantity of y with respect to changing the in customer's income. Okay. And negative px x x y and negative 1 0 0. Okay. Look, again, the best way to solve this is through Laplace expansion. Then we get this as negative 1 over h times negative px negative py u x x u x y, or after calculations u x y p x minus u x x p y over s. And look, identical situation, right? This part is positive, this part is positive. However, this part is indeterminate. Okay, but look, let's just say that we are dealing with normal goods, right? We are dealing with normal goods. If we are dealing with normal goods, we can safely assume that this is positive. Okay, in this scenario, both comparative static derivatives are going to be positive. Therefore, how would we solve increase in customer's budget on the graph? Look, how do we make a budget line? To get this point, so point where customer spent all his money on good Y. In order to get it, we simply divide the budget by the price of good Y. Right? If we got some budget, we divide it by some price, we see how many units we can buy. And the same over here. We check how much money we have, we divide it by the price of the good we want, and this is how many units we can get. Now, as budget increases, we are dividing the bigger number. Oh, let's use 1 and 1 and 2 here. So we are dividing bigger amount of money by the same price, of course we are able to buy more units. And similarly, we would see it over here. And consequently, increase in budget leads to the movement of the budget line outward, right? In a parallel motion, right? Because the price ratio is not affected by increased budget, so we simply see a parallel movement upwards. And look, of course, now as a result, customer can get on the indifference curve that is higher, and we see that given that both goods are normal or luxury, we would see this as our customer purchasing more of good X and more of good Y. Okay, so look, now we know how does budget affect customer's choice. In the next part, we're going to use the framework that we have used to analyze budget, but this time we're going to examine what are the consequences of changes in prices of one of the two goods. Thank you for your attention. See you in the next video.